Hey everyone, welcome to your solution video, just double checking some extra practice problems. In the first, number 31, we're to match the description to one of the compounds lettered E through H. And it might be just rich of an idea to review an amine versus an amide. And so thinking that through, the amine, which we have been studying in this current chapter, of course, has the nitrogen just next to an R group. There is no indication of a carbonyl. So the amine can be primary, secondary, tertiary, but the nitrogen itself attaches directly either to a hydrogen or to a carbon. But the amide, do you remember its qualifications? It had to be directly next to a carbonyl carbon. And so this was the function of looking at the amide. To tell them apart, you really need to look at the next position. If you have a carbonyl, it's an amide. If it's just next to an ordinary carbon, it's an amine. So that's really the focus of just reviewing last term, chapter 17 information, and with the new concepts of amine chemistry in chapter 18. So which one did you choose that contains a primary amine and a primary amide? When you looked through those, I found that to be letter H. And letter H, if we just kind of stick with our same highlighters, to find the primary amine, this I'll color code in green to match the primary amine category, and I'll use blue right here to represent the primary amide. The nitrogens are attached to just one carbon. Yeah, that's right. I was pausing there just because the NH2 group was throwing me, but it's attached to just one carbon. So there you have letter H. How about B, a compound that contains a primary amine and a secondary amide? Well, did you find structure F? When I look here, and again, just kind of color coding with the same colors here, the amide I'll do in blue. Here is the amide. It is directly attached to two carbons in that particular case. So just one hydrogen on that makes it a secondary amide. And the primary amine color-coded here. So that is letter F for this question. Compound that contains a secondary amine and a tertiary amide, that was letter E, and leaving this for G. So let's kind of just go through and make sure we see those. A secondary amine, the amine right here, color-coded in green as secondary. It's attached to two other carbons. And the amide is this functional group. That nitrogen is attached to three. And then here, the letter G, a compound that contains a tertiary amine and a tertiary amide. This is the color function of the amide. And again, this is your color coding function of the amine. Tertiary on both counts. Alrighty. Oh, a little nomenclature practice. In letter A, let's start there. We're just simply asked to give an acceptable name, so we can use common names when appropriate or IUPAC names when appropriate as well. I noticed that these are the exact same groups, so I'm sure you named that as diethylamine. This looks like a 1, 2, 3, 4, 5, 6, 7, 8 carbon chain. And on carbon 3, we have the amine. 3-octane amine. How about letter C? 1, 2, 3, 4, 5, 6 carbon chain and the longest chain. And there is a methyl group hanging off of one of those nitrogen bonds. So we'll identify that with N-methyl. Give you the location that at carbon 3 of a 6 carbon chain, there is an amine group. And here in letter D, here is an ethyl branch And how many altogether? 1, 2, 3, 4, 5, 6, 7 altogether. So we have N-ethyl. And at carbon 2 of a 7-carbon chain, they have an amine. Putting it all together, it simply sounds like an ethyl 2-heptane amine. Let's try 37. Drawing structures corresponding to each name. Well, letter A is a long one, isn't it? A 10-carbon chain. This could also be called decylamine, just as its common name as well. So you would have a 10-carbon chain, CH3, CH2, and I'm going to just put that in a parenthesis. How many we would need to take? We'd need to take, well, 9 of them to get 10 carbons, because the ending chain would be an NH2 group. So that's literally 10 carbons in a row. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, terminating with the amine group, a 10-carbon chain with an NH2 at the end. How about B? Tricyclohexylamine. Just drop my pen. Here we go. There's A. How about a letter B? I'm going to put a nitrogen in the center, and a cyclohexane is coming off of each of those nitrogens. There's 1. All right, we're drawing a cyclohexane in all 3 directions, making sure we see that there's 1, 2, 3, 4, 5, 6 membered ring, and of course a lone pair of electrons. Tricyclohexylamine. Para-bromoaniline. Well, I remember the aniline with its 6-membered aromatic benzene with a nitrogen coming off to give it the aniline name. And a para is a 1,4 position, so I'll call that carbon 1, 2, 3, 4. Then we have a bromine coming off of carbon 4. Para-bromoaniline. Letter D. 3-amino-butanoic acid. Butanoic. That's our carboxylic acid functional group. We need to remember, don't we? So that means we have a 4-carbon, and I know that the carboxylic acid is at the terminal end, butanoic acid. And at carbon number 3, we would have the amine group, the NH2. 3-amino-butanoic acid. How about letter E? NN-dipropyl 2-octane amine. Well, I hear that 8-carbon parent chain. 2, 3, 4, 5, 6, 7, 8 carbons. At carbon number 2, we have the amine, and it says it's dipropyl, NN, telling me that it has 2 groups of propyl groups coming off. 1, 2, 3, 4, 5, 6, 7, 8. The longest carbon chain is the parent name. And then these are the alkyl groups called propyl. And there's 2 of them. And so we're labeling that as dipropyl. Since not all 3 of this tertiary amines groups are the same, we must use N, N dipropyl 2-octane amine. And let's squeeze another one on here. Letter F. N-ethylhexylamine. So that means the parent is 6 carbons. And since I have an alkyl common name, that means I'm hearing hexyl. That means that I know that it's going to be at the terminal end, that it's a primary at the end of the carbon chain. So hexylamine is 1, 2, 3, 4, 5, 6. That's hexylamine. Now what's attached to it? Oh, attached to one of the nitrogen bonds we have an ethyl. So that would mean just 1 hydrogen and an ethyl group going in the other direction. N-ethylhexylamine. How did you do? Oh, I bet you're doing great. Let's keep drawing. Let's draw the structure for each ammonium salt. And remember, ammonium salts have quaternary nitrogens. 4 bonds. So letter A, I'm going to get my nitrogen, and I know it's going to have 4 bonds, so I'm just kind of getting those bonds ready. Alrighty. Dipropyl. Alright, so 2 of the 4 bonds will have propyl groups. Now I'm just putting them there. There's the dipropyl part. And then it says ammonium chloride. So that means the other 2 bonds must be going to hydrogen, and that's your positive charge, and the chloride would be negative. Dipropyl ammonium chloride. How about B? Again, I'm going to put my nitrogen in there, remind myself that has 4 bonds to be an ammonium ion. And it simply says butyl ammonium bromide. So I have 1 attachment to a 4-carbon chain, that's your butyl, meaning that 3 of the bonds have to be hydrogens, and you would have a plus, and then the negative name is bromide. And letter C, ethyl dimethyl ammonium hydroxide. Well, let's get your nitrogen there. We know it has 4 bonds to be an ammonium ion. One of those is a 2-carbon chain. I hear ethyl. 2 of them are 1-carbon chains because I hear dimethyl, and then ammonium. So that means that this 4th bond must be the hydrogen, and the last name is hydroxide, OH negative. Ethyl dimethyl ammonium hydroxide. You have a positive ion and a negative ion making the salt. Let's draw some hydrogen bonding between 2 molecules of diethylamine. Diethylamine. So 2 of the bonds are going to ethyl groups, and 1 of the bonds is going to a hydrogen group. This is diethylamine. The criteria for hydrogen bonding is to have a hydrogen attached to the nitrogen, and there it is right there. So we have 1 position of hydrogen bonding. And that means the interaction between molecules, well, the nitrogen from 1 molecule is going to communicate with the hydrogen of the other molecule. Those are based on opposite charges. Let me just take a red pen and draw the actual hydrogen bonding. They're going to have a dashed line represent the hydrogen bonding. So the nitrogen of 1 molecule is attracted to the hydrogen of the other molecule. And you're going to show that right there with the hydrogen bonding as the dashed line. Perfect. Not a true bond, but an intermolecular attraction. This is a secondary amine. Each one of these molecules exhibits 1 area of hydrogen bonding. The nitrogen on 1 is bonding, hydrogen bonding to the hydrogen on the other. Okay, let's keep tracking. Here we have some acid-base chemistry, a proton transfer. When I think about proton transfer, we form conjugate pairs. Here we have a nitrogen that is a tertiary nitrogen, just kind of getting that straight in our minds. This nitrogen is bonded to 3 carbons. So I could see that. I'm going to just come down here. I have a 1, 2, 3 carbons leading to nitrogen, leading to a methyl group. Alrighty, and here's your lone set of electrons. So this would be N, N, dimethyl, propyl, amine. And we're going to react that with hydrochloric acid. And I'm going to stress mechanism. The nitrogen reaches out for the proton, the base, and the acid. The acid is the proton donor. The base is the proton acceptor. The arrow originates at the base and goes toward the acid, and this bond collapses. Now on the product side, we have the conjugate acid. We have a 1, 2, 3 carbon chain, and now we have a quaternary nitrogen that's going to carry a positive charge, and the conjugate base forms the chloride as well. So this positive ion, you'll probably see it inside of a bracket with the positive outside, but the positive charge is on the nitrogen. The name of the salt we just formed would be N-dimethyl propyl, I ran out of room, ammonium chloride. It's all one word. I just ran out of room there. N-dimethyl propylammonium, and then the last name chloride. All right, how'd you do? Letter B. Letter B gives me a primary amine, NH2. So I'm just finding this nitrogen here. The nitrogen is attached to 2 hydrogen. So this guy here is just on 1, 2, 3, 4, 5 carbon chain. We have a 3 pentane amine reacting with sulfuric acid. So I'm going to draw my 1, 2, 3, 4, 5, and the nitrogen now is quaternary. So the proton adds on to the nitrogen, leaving HSO4 negative. Remember, just one proton transfers. So you could write this if you'd like to, just to get the habit. You could write that NH3 and the plus right there on the nitrogen and the HSO4 negative. A proton has been transferred from the acid to the base. Here's the nitrogen in this aromatic compound. It's going to abstract the proton, and this bond collapses. The conjugate pairs form. The nitrogen now inside of this aromatic ring is attached to that extra hydrogen, creating the conjugate base of bromide. This needs a positive sign on the nitrogen. And now here we have a cation, which acts as the acid, and this now is the base. So the proton that's going to be transferred from the base to the acid. Remember, the sodium is just a spectator. So just think of that as OH negative, and this is the proton that's going to be abstracted, and then this guy, the bond collapses. So we come out with CCN, 2 carbons in each direction, and the conjugate acid of hydroxide, which is water, and then of course the sodium is just migrating as a spectator ion. So the cation went back to the original amine. And just thinking about naming that, see how we have triethyl ammonium, to say that it's a quaternary nitrogen, triethyl ammonium ion reacting with hydroxide ion. You formed an amine, which would be triethyl amine. Plus water. And again, the sodium is just there as a spectator. Beautiful work. Shall we keep going? We have one last slide to check together. It's number 52. Which ammonium salt forms when each is treated with HCl? So these are going to be proton transfers. On the product side, we will form a quaternary nitrogen, meaning the NH3 plus and the Cl negative will form. A proton has been transferred. How about in letter B? Here we have our proton transferring. Here's a carbon leading to the nitrogen. So right here you'd have NH2, CH3, and the nitrogen carries the plus sign. And of course you'd have Cl negative. We made a quaternary compound. If you want to see like letter B, if we just maybe take our time and see really what's happening. Here's the carbon, it's 2 hydrogens leading to a nitrogen, leading to a set of carbon. So that when HCl, when we have a proton transfer, notice it's this site right here. This is the proton that gets abstracted and this bond collapses. And that's why when we redraw this original carbon, now you have a nitrogen attached to 2 hydrogens, giving it a formal charge of +1. That's kind of just the structural idea there of letter B. And letter C, here you have your aromatic compound, alternating double single, double single. Trying to make that a little neater. There we go. Leading out to the nitrogen, so keep in mind this has 2 groups of carbon on it, and then here's where the hydrogen would go. It's the 4th bond, and then of course Cl negative. So you could see that written as, in its condensed structural formula. When you write that out, you could put NH parentheses CH2 CH3 taken twice. Just make sure you remember to put the positive charge on the nitrogen because it now has 4 bonds. Quaternary ionic salts. Perfect. Oh, I bet you did great. Hey, you made it through chapter 18. I'm proud of you. When ready, I'm looking forward to reading all of that great, your notes from the pulling out of the sections of your connections there to the health and medicine, as well as some neurotransmitters. And then just put this into the Dropbox when it's 100% ready.